Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. This is the fifth lecture in the series. In the previous lectures, we have seen the concepts of electrostatic force, electrostatic field and the related concepts. And in today's topic, we are going to see the concepts related to electrostatic potential. And the session outline is going to be electrostatic potential, mainly the definition and the relation between electrostatic potential and field, potential due to a point charge, potential due to a charged spherical conductor and potential due to a spherical charge distribution. We will first define what is electrostatic potential. It is defined as the work done in bringing a charge from a infinite point to that point. We will see the definition once again in detail. The potential difference between 2 points in an electric field is defined as the amount of work done in moving a unit positive charge from one point to the other point against all electrical forces. Here the expression the difference in potential is given as the difference between the potential at 2 points is the ratio of work done to a unit positive charge. In the same line, if you define the electric potential at a point, not the difference here, at a point in an electric field, it is defined as the amount of work done in moving a unit positive charge from infinity to that point against electric forces. Here what we have assumed is, according to this expression, the potential is also equal to the potential difference, but the initial point is supposed to have 0 potential. That is the meaning of the word infinity here. It is not just the distance infinity, it is a point where the electric field is 0 and thus the potential is also 0. So, the electric potential at the point is defined as the work done in bringing a test charge from infinity to B. The symbol infinity to B is represented here per unit charge. The unit of electric potential is joule divided by coulomb and it is given a new unit called volt. So, the unit of electric potential is volt. We can also derive a relationship between the electric potential and also the electric field. For that we have to consider how the force applied is doing the work and the related concepts with an illustration. So, let us take an illustration and try to understand how the work done is related to the potential and thus how the potential is related to the electric field. So, let us take this illustration and discuss it elaborately. Relation between electric field and potential, that is the main aim of this derivation. So, we consider the electric field is existing in space as represented by these dark solid lines and we take a unit positive charge which is represented here. It is moved from the point A to the point B on the path which is shown by a dotted line here. and we apply the force which is represented by this vector F, and the displacement is also along the direction A to B. At that point its tangent is represented by the vector dl, and when we apply the force and make it move along the dotted path, the electrostatic force is just opposite to the direction in which we apply the force. So, we first try to get a relation for finding the work done. We know the work done is the dot product of the force and the displacement. So, it is F dot ds, or in scalar form when we want to mention it, it is F ds and cos theta. Let us try to use the concept that we are familiar in mechanics to find out the work done in this case. So, work done in moving the charge from A to B is defined by this definition F dot dl. F is the force, dl is the small displacement. So, we are integrating it to find out the entire work done. We would like to replace the force that we apply by the electrostatic force that is existing. So, it is Q naught into E. This expression is also familiar to us, and there is a minus sign. This minus sign says the applied force and the electric field are opposite to each other, and we try to bring the Q naught to the denominator because that is only is a definition of the potential or potential difference. So, we get an expression for the potential difference in this form. In this, if you take the point A to infinity where we assume the potential is 0, so we get the expression for potential itself in terms of the electric field as illustrated here. It is read as negative of integral E dot dl, and E and dl are vectors here. So, this is the relation relating the potential and electric field. The same expression can be represented in the differential form. When we differentiate it on both the sides, we end up getting this expression. Here the r cap is representing the unit vector. We will see why we need to use this r cap here. It has got a significance. We will see it in the course of the lecture. So, these two expressions we are supposed to remember as the relation between the electric field and potential. Having established the relation between electric field and potential, we can use the same expression now for finding the electric potential, electrostatic potential due to a point charge. We will try to use the relation right now we have established. The potential due to a point charge. We very well know the electric lines are coming out from a positive charge. So, that is representing the electric field itself, and we are bringing a unit positive charge from the point A to the point B. So, we need to apply a force which is represented by the blue vector here. The electrostatic force is represented by the green vector here, and the direction in which the charge is moved is represented by the red color vector, which is representing the infinitesimal displacement dl. So, we write the definition that or the relation right now we have established the relation between the potential and the electric field as the potential difference Vb minus Va is equal to negative of integral E dot dl. The beginning and end points are mentioned in the integral as the limits, and we try to replace the vector into a scalar form, replace the vector form into a scalar form. So, we have to write the cos theta for it. Here the theta is pi because that is the angle between the electric field and the displacement vector. And in the simplification, cos pi, cos 180 is negative, is minus 1. So, minus of minus becomes plus here, and one more replacement is required. When we take the term dl, it is measured from A to B, but we take the positive charge as our reference. So, we take the distance from the positive charge to the point where we are bringing the charge, test charge. So, it is better to introduce the term dr instead of dl, and this is the relation between dr and dl. Why there is a minus sign introduced here? It is because as the value of dl increases, the value of dr will decrease. They both are inversely related as far as the change is concerned. So, based on that we put a minus sign. So, once again the minus sign comes here, we get a relation after we introduce a term for E. E is 1 divided by 4 pi epsilon naught q by r square. This relation we already have come across in the previous lectures. Now, we have to carry out the integration to find out the electrostatic potential. Let us do the integration now. So, mathematically the integration is carried out here. We end up getting dr by r square inside the integral sign, and the q 4 by epsilon naught are all taken outside because they are constants, and this is the value of the integral, and we apply the limits, and finally we get this as the expression for the potential difference between the points B and A here. So, this is the final expression for the potential difference between the 2 points. But our main aim is to find out the potential at a point, not just the potential difference. So, as we have done in the previous case, take the point A to infinity. In that case, the potential at the point A becomes 0. So, the expression also gets modified accordingly. So, we put V A as 0 because the point is taken to infinity, and the R A is also taken to infinity. 1 divided by infinity is 0. So, this term totally vanishes, and finally, we get the expression for potential at the point B as a simplified form as highlighted here. So, V is the potential at the point, a distance r from the charge q, and this is the expression for the potential. It is found to be inversely related to the potential as far as a point charge is concerned. So, we have right now derived an expression for potential due to a point charge. Now, based on the value that we have obtained, let us try to understand the characteristic features of the potential. The first point that we should keep in mind is electrostatic potential is a scalar quantity because it is a work done by unit charge. So, work done is a scalar. So, electrostatic potential is also a scalar, and the potential near a positive charge is positive. It is because of the work that is done to move the positive charge, test charge, from infinity to that point itself is positive. So, the potential near a positive charge is positive, and in the same way potential near a negative charge is negative. If the potential is due to several point charges, then the total potential is the algebraic sum of the individual potentials. So, we have to find out the algebraic sum. V is equal to V1 plus V2 plus V3, but one point we have to remember here, when we take V1, V2, V3, they can be positive or negative based on the charge for which we find out the potential. So, that is why the word algebraic sum is used here, and if the potential is due to a distributed charge, the charge is just distributed over a particular conductor, then we have to take the integral for that. So, the total potential is nothing but the infinitesimal summation or the integral value of the potential due to small parts of the distributed body. We can use this expression V is equal to integral dV to find out the potential due to a sphere and distributed charges. The potential due to V is equal to integral dV to find out the potential due to some distributed charges like spherical charge distribution or charged conductor like objects. As an example, we will take the potential due to a spherical charged conductor. Let us take a charged conductor which is used as a distributed charge to find out the potential due to that distribution. We very well know the excess charge resides only on the outer surface of a conductor. So, here we have taken a conductor which is of radius r, the excess charge resides only on the outer surface. Hence, it can be even called as a shell, charged shell. So, the charge is absent inside, it is only on the outer surface. We are going to find out what is the potential due to this kind of charged shell at points outside, inside and on the sphere. So, for that we are considering certain geometrical parameters of the charged shell. The first point is its surface charge density is sigma, the charge per unit area is sigma, and we are taking a small elemental shape which is cut as a slice in the charged shell. So, we will mostly get a shape which is more or less a ring, a uniform ring. So, that is represented between the two lines here, that also subtends an angle theta with the reference axis, and the thickness of the ring subtends an angle d theta. It is all illustrated in the diagram. Thus, the radius of the ring, which is an elemental part of the sphere, is r sin theta as per this triangular consideration, and this becomes the segment in the section. So, this the thickness of the segment becomes r d theta. We choose a random point P at which we want to find out the potential due to this sphere, and the radius is r, and we make the measurement from the center of the sphere to the point P. So, this is the geometrical consideration for finding the potential due to a shell. Based on the geometrical construction, let us try to establish the relationships to find out the potential due to the entire ring, as it is illustrated here. The area of the ring is nothing but the radius 2 pi r sin theta into r d theta. Here r d theta is the thickness of the ring, and we have already stated the charge per unit area is sigma. So, dq is taken as the small charge that is present on the ring. So, we multiply the area with the density, charge per unit area, and we get an expression for the charge on the ring as this, and we are now substituting for sigma, and we simplify to get a final expression in this form. It is 1 by 2 q sin theta d theta. So, this is the elemental charge present on the elemental ring. Now, each dq is at a distance x from the point P that we have considered. So, the elemental potential at the point P due to the elemental ring is given by this relation dV, which is 1 divided by 4 pi epsilon naught q by x. Here the q is the elemental charge. So, we write it as dq divided by x. X is the distance between the ring and the point. If you want to have a glance at the construction, we can go to the previous slide and see what is x. The x is the distance between the ring, each part of the ring to the point P, and we get the expression for the potential, infinitesimal value of the potential at the point P due to the elemental ring is this expression. Now, we go for some geometrical consideration, so that we can replace the value of x with the measurable values like small r, which is the distance from the center of the ring, center of the sphere to the point. So, this is a geometrical relation, but we want to have the d theta term, sin theta d theta. So, we differentiate this expression and try to establish a relation for sin theta d theta. So, the sin theta d theta is found to have a value x dx divided by 2 capital R small r. Here capital R is the radius of the sphere and small r is the radius of the it is the distance from the center to the point P. Now, we have found certain terms to be replaced in the regular integral and try to use those relations and try to do the integration. After the values are substituted, the expression for the dV is obtained in this form 1 divided by 4 pi epsilon naught q dx divided by 2 r r. Now, we have to integrate it keeping the points in mind, which point we are interested in finding the potential. The first point is an outside point. So, we choose the limits for the integral from r minus r to r plus r. So, when we take this limit, it will cover any point which is outside the shell. So, we carry out the integration. All the terms are found to be constants, the q, r, capital R, 2 and 1 by 4 pi epsilon naught, all these terms are found to be constant except this dx. So, we keep the dx alone inside the integral, then we take all the other terms outside the integral and we carry out the integration, and after substitution, after integration and substituting the limits, we finally get this as the expression for the potential outside the sphere. When we look at this expression appears so familiar to us because it is nothing but the potential due to a point charge. So, what is the conclusion? The conclusion is, for a point which is outside the shell or a spherical charged conductor, the conductor itself is acting as a point charge. So, that is the inference we get from it. For any point outside the sphere acts as a point charge as if its entire charge is concentrated at its center. Now, we will take the other point which is on the sphere and also a point inside the sphere. For on the sphere, we have to just replace the small r with capital R because capital R is the radius, and for a point inside the shell, we have to change the limit for the integration from capital R to capital R minus small r to capital R plus small r, because this will cover the entire region of the shell, but for a point inside the shell. The same way we carry out the integration except for the limits, and what we get is a term which is also somewhat familiar because the previous expression on the sphere, what we got, the same expression we are getting. So, it is 1 divided by 4 pi epsilon naught q divided by r. Here this r is the radius. So, what is the conclusion? The conclusion is, what is the potential on the sphere? The same is the potential at any point inside the sphere also. So, for all the points inside a spherical shell, the potential remains constant. This is further understood by just plotting a graph as like this. So, this is a graph showing the potential versus the distance measured from the center of the shell. Just for the reference, the shell is also shown here. For any point which is inside the shell, the potential remains constant. For points outside, the potential falls inversely. So, this graph clearly says the potential inside the shell is constant. Now, we will continue to use that expression for finding the potential due to a charge distribution. In charge distribution, the potential, the charges reside inside the distributed area, inside the distributed volume. So, let us take up one such charge distribution and try to establish a relation for the potential. Charge resides inside a non-conducting sphere. So, probably we may have to choose a non-conducting sphere which is charged. So, charges are found to be in the inside region also. The expression for V is the same as that of the shell for a point outside and on the spherical distribution. We need not do these calculations once again because the value will be the same for a point outside and also for a point on the spherical distribution. To find the V inside the sphere, we use the expression for electric field. This expression we have already established in the previous lectures. The electric field, using the Gauss law, we have obtained this relation. E in spherical distribution is 1 divided by 4 pi epsilon naught q divided by r cube into small r. Here capital R is the radius of the sphere and small r is the distance measured from the center of the sphere. Now, we will try to use the relation between electric field and potential to find out the potential at a point inside the spherical charge distribution. So, we write the expression, just now we have seen a relation relating potential and the electric field. This is the relation, main relationship we are going to use. So, we write it for our case. These are the 2 points we are taking. C is on the sphere and D is inside the sphere. We are interested in finding the potential at the point D, which is inside the sphere. So, we find out the potential difference between the 2 points C and D using the relationship V D minus V C is equal to negative of integral E dr. So, we substitute for the E, which we have already derived, and we take the integral limit from capital R to small r, because from outside to the point inside we are doing it. So, when we integrate and apply the limits, we get this as the final relation. We know that V c is the point on the sphere, as it is shown, the C is on the sphere. For on the sphere, we already know this as the relation, it is 1 divided by 4 pi epsilon naught q divided by capital R, and when we try to use this V c and rewrite the expression for V d, finally what we get is this relation. In this, the small r is nothing but the distance from the center of the sphere to the point. We write this as the expression for the potential at a point inside the sphere, it is 1 divided by 4 pi epsilon naught q divided by 2 r, and within bracket we have a constant 3 appearing, and then minus r square by r square. The capital R is the radius, small r is the distance from the center, the small r is the variable here. As we have done in the previous case, that is a shell, here also for the spherical distribution we would like to draw a graph for the potential versus the distance measured from the center of the shell to any point outside, and what sort of graph we are getting when we plot. This is the graph we are getting. The V at the center is found to be this 3 by 2 V naught. We have to substitute small r is equal to capital R in the previous expression. We end up getting this as the expression. So, the potential at the center seem to be the maximum, and then it falls according to that relation, and on the sphere it is found to be V naught, and after the point considered on the sphere, when we move on to the outside point, it is varying inversely. So, we have got the expression for potential due to a spherical distribution at a point on the sphere, outside the sphere, and finally inside the sphere at any point, and this is the expression for potential at the center of the sphere. Now, we will see the summary of this lecture. We have seen the following concepts in this lecture: definition of electrostatic potential and potential difference, the relation between electric field and electric potential, the properties of electrostatic potential, the potential due to a point charge, the potential due to a charged spherical conductor or shell, and potential due to a spherical charge distribution. We have also established some sort of graphs for the potential versus the distance from the center of the shell. Having learnt all this, now we will try to check our understanding by answering these questions. Define the electrostatic potential and mention its unit. What is the relation between electric field and the electric potential? What is the expression for V, that is potential, near a point charge? Discuss with expressions the potential at points outside, on and inside of a charged spherical conductor. Get the expressions for potential outside, on and inside a spherical charge distribution. We have seen the concepts of electrostatic potential at length. We will try to learn further concepts in electrostatics, like the concept of electrostatic dipole, in the subsequent lectures. Hope you enjoyed this session. Thank you.